All right, last thing we are doing in this unit is something very different. We spent a few days sketching, moving on to something different. This is a trick to differentiate different kinds of expressions using logarithms. Um, Not even a few of them we're going to see are going to be exponential, which is a common thing that when we're dealing with an exponential expression or equation or function, whatever, that is tricky for some reason. We'll rewrite it in exponential form, something like that. It's not what we're doing, but it's common that we would use logarithms to simplify an exponential expression. That's something we've seen, but that isn't the only place that this is useful. Okay, this is a trick or a tool that we can use in differentiating expressions that can be used to simplify things or make things possible that otherwise wouldn't be possible in different kinds of cases. So it's really fantastic. So it's different from other stuff that we've done in the unit, but it's a really important skill. And it's called logarithmic differentiation. And notice that it says for each of the following, determine dy by dx. We are not going to leave an implicit form, at least where it's possible, which most places, if not all, it will be possible. We are going to write in explicit form, not implicit. We usually do leave an implicit, but in this case, we will be able to make it explicit. And that sounds like we're talking about a certain kind of differentiation, doesn't it? Which this doesn't look like implicit differentiation. And it doesn't look like that, but it's sort of hidden, okay? Okay, so let's give this one a try. Why is this trickier? Why is this, what's wrong with this? Well, if I just threw this at you, so I'm not going to do this, here's what I would imagine people would try. People would try y prime equals, well, I'll bring the exponent down, then I'll subtract 1 from the exponent. So it'd be 3x squared minus 1, I guess. Oh, maybe we do it times the derivative of the exponent as well. Well, good guess, maybe. It seems to make sense, but it doesn't. Similar to product rule is not just take the derivative of one and take the derivative of the other, right? It's got a whole process to it. Well, this is kind of like a product rule, but with exponents, where I've got base is a function and the exponent is a function. We've not quite seen something like this. So this is definitely incorrect. Please don't ever do that. We don't subtract 1 from an exponent that is a function. Okay. So what do we do? Well, when we have a function in terms of x raised to an exponent in terms of x, so we have a variable in the base and a variable in the exponent, what we're going to do is we're going to take the log of both sides. And if we're taking the log of both sides and we're going to do the derivative, what base do you think we want to choose when we take the log? So we're going to take the log base e of both sides. Why does this help? What can I do now to simplify this? What awesome property of logarithms can I use to simplify this? I can bring the exponent out. And way back when, the first time you learn this in MHF, I mean, for my classes, I make a big deal about how unbelievably awesome this property is, and I cannot explain further. I cannot stress enough to you how useful this trick is. And we saw it in MHF how useful it was, but man, look at that. That is unbelievably useful. And now we have to take the derivative of this, and that's why it's implicit, because now I have a function in terms of y on the left side. And when I take the derivative of that, it's 1 over the argument times the derivative of the argument, which is dy by dx. And that's going to happen a lot, so get used to that, because often we just have ln of y on the left side, because a lot of these, if not all of them, are going to start as y equals. On the right side, I have product rule. Derivative of the first thing times the second thing plus derivative of the second thing times the first thing. So dy by dx equals, multiplying both sides by y, clears the 1 over y on this side. So I get y big square brackets, and I can simplify anything on the right side if I want to. And in this case, 3x squared over x is just 3x. And I'm not leaving it in implicit form. This is implicit. But in this case, notice I don't have a whole bunch of junky y's in there. I don't have some kind of crazy implicitly stated function on the right side. I only have this one y. So what can I do to write this explicitly? Well, we know what y equals. It equals x to the 3x squared. So I can replace this as x to the 3x squared times all of this. And that one doesn't look too bad. I could factor that and simplify it even a little bit further, maybe even kind of solve it. I don't know, solving this may not be something we know how to do, but I could manipulate that a little bit, but we're not going to. We're just going to leave it. I'm going to make a little note here off to the side. Note: when you have a variable in the base and a variable in the exponent, take the log of both sides first. Then differentiate. And probably, and by probably, I mean definitely base E. There might be occasions in mathematics where you don't want to use base E, but for us, we're going to use base E because otherwise we'd have that annoying constant in all of that, right? So why would we do that? So we do base E, taking the ln of both sides, and that's going to make our lives a lot easier. All right, and we're going to do a few more examples of these, and that's basically it. So same thing, I've got, this looks like crazy, x to the cos x, oh my goodness, but I'm going to take the ln of both sides. And so that brings the cos x down from the exponent, ln x, and again I have product rule. So derivative of ln y is 1 over y dy by dx. Anybody remember the derivative of cos? Derivative of ln x. Isolating for dy by dx. Again, we get this y cos x over x minus sine x ln x, and then replace y and that's not going to simplify any further, and we're done. And it seems like a long time ago now, boy, but I remember when we first did implicit differentiation, and I talked about how there was going to be a time where we wouldn't leave it in implicit form, and this is the case because all we have is that one y, so I can replace it with what y actually equals, because all of these questions start with that y equals, as I said before. So I remember talking about that where we had questions that had a whole bunch of junky y's in them. Let's see how easy it would be to find one of those. Here's our lesson on implicit differentiation. This is what I mean. Replacing each one of those things that one only has 2, but this wasn't stated in terms of y, and we can't solve that for y. We can't solve that expression that we started with for y, really. There it is in focus. So it's just not worth it. So that's why we couldn't do it before, but with these ones we can. They're very different. And so where we can, it's a good idea to rewrite in explicit form. We were given the question in explicit form, so generally we can probably leave our answer in explicit form, right? All right, same thing. Go ahead, pause the video, try this one on your own if you like. Again, product rule, derivative of the first thing times the second thing. Plus derivative of the second thing, 1 over, or let's just make it 3 over 3x minus 4, because I don't know that we've really done that before, but this is probably what you do. Take a look at what the inside is, the argument is. The derivative of that's just going to be 3, so I can sort of save myself a little bit of trouble by just having it out front there, times the first thing, which is 4x cubed. Okay. So dy by dx equals y times 12x squared ln of 3x minus 4. And then the 4x cubed gets multiplied with the 3. Whoops. So I get 12x cubed over 3x minus 4. And then replacing the y with the 3x minus 4 to the 4x cubed times all of the rest of that stuff. Okay. Again, it looks like I could easily factor out a 12x squared, but these things generally are too hard for us to solve, so we're not usually doing anything with these. Like, we're not doing any more sketching. This is the end of the unit. We don't do sketching with this stuff, so don't worry about that. We don't generally try to factor what's left, but you know, by now that's probably just something we notice and we can't help ourselves, right? So, and I would imagine a lot of people wonder, are we supposed to factor where possible? But for these, no. All right, one more of these. Okay, so what do we do every time? We take the ln of both sides. And now take the derivative, 1 over y, dy by dx. This is 2x times ln of root x, so the derivative of 2x is 2. Again, it's product rule. These always work out to product rule, right? Plus derivative of the second thing. So 1 over root x times the derivative of x, which is 1 over 2, times x to the negative 1/2, times the first thing, which is 2x. So the 2 from the 2x and the 2 from the half are going to simplify. Equals y, 2 ln root x plus 1 over root x. The half is gone. This is 1 over root x. The 2 is gone, times x. Dy by dx equals, I can replace y with root x to the 2x times 2 ln root x plus 1 over root x times 1 over root x is 1 over x times x is x over x. And that obviously works out to 1, and I would rewrite that as 1. Excellent. Now hold on. Let me go back up here. Anybody notice anything about this? Whose skills with exponents and properties of exponents are sharp? What if I did this? Remember, when I'm taking a power of a power, I multiply the exponents. So if I have a product in an exponent, I can split it up to a power of a power. Well, what is that? What's the square root of x squared? X. Aha. Is that going to be easier? Well, let's try it and find out. Now, everybody's going to have a little panic here and ask, well, wait a minute, is that something we have to do? Do we have to simplify first? And how am I supposed to know when it's going to be better to simplify first and when it's not? Well, you don't have to. Practice will let you know when it's easier. And some people are better at noticing these things than others. It comes naturally to some people, and other people maybe have to work a little bit harder for it. In the end, you can get to the same place, but you might not. So let's finish this one, and then we can talk about which one's easier, and we can compare the answers, and we'll talk about this a little bit further. I'm going to do the same thing where I take the ln of both sides, and I'm already thinking that this way is going to be quite a bit simpler. Because the derivative of the first thing is just 1 times the second thing plus derivative of the second thing, which is 1 over x, times the first thing, which is x, dy by dx equals y, ln x plus x over x, dy by dx equals, replacing y. Now I could, I guess, replace y with that, x to the x times ln of x plus 1. Or I could have replaced it with the original one, but why not use a simpler version? So those aren't the same. And what if this is the answer in the back, at the bottom of the worksheet, but I get this answer? Is that wrong? Well, no, it's not wrong. So there are going to be cases where your answer might look a little bit different, okay? And that is troubling. I'm sure you would have at least done this, right? Equal to 1. You would have done that to 1. There's a reason why I didn't do that yet. So you have to take that with a grain of salt. Again, you can use technology to check your answer if it doesn't look exactly the same, but you think you haven't made any mistakes, or you can ask and have us look it over. If yours is different, you can go back and see if there was some kind of trick to simplify at the beginning. Okay. A really good thing is to check it with technology and see if your answer is the same as the answer that's given. Okay, of course, sometimes there's mistakes in the answers, so that's something to think as well. Regardless, what would happen if I simplified this further? So I could still split this up and make it x to the x, because that's just the same as what I did above. So dy by dx. If I hadn't noticed it first, I might not notice it now. But if I see the answer like this, maybe that would help me notice it. Again, I don't know. But this is going to be x to the x. And this is going to be ln of root x squared, bringing the 2 back into the exponent, right? Whoops. Plus 1. So that's why I didn't do it before, because I was going to do a little bit of extra work anyway. X to the x ln of x plus 1. And now they do look the same, but there's no reason why you would necessarily get to this step and do that simplification. You would do the 1, I imagine, but not the rest of it. So your answer is going to look a little bit different. But this is easier, so it's worth trying to notice these things. How do you know if it's going to help? You only know by trying. But I took something that's got square roots and a bigger exponent, like a more complex exponent, into something that sure looks a lot more simple. So I imagine that the derivative is going to be more simple, and it turns out it is. And again, that comes with experience, okay? So that is all stuff to just keep in mind. But generally speaking, if this was a question on a test, we would be aware of the variety of answers that you could get, whether you simplified or not, and both would be acceptable answers. Okay, leaving something like x over x, that wouldn't be, but the rest of the simplification would be fine. Okay, and that is logarithmic differentiation. Like I said in the very beginning, like we noticed, when you have x or whatever variable, but generally x in the base and in the exponent, we use logarithmic differentiation in order to do the differentiating. So it's a very useful skill, this logarithmic differentiation. It allows us to take the derivative of things that we otherwise really couldn't. Okay, got one more example here. This is just something to try that will, be a little bit more challenging now that we've been taking derivatives for a long time. Why is this challenging? Well, it's got a product in the numerator. It's got a product in the denominator. It's got a numerator and a denominator. So this is quotient rule, but both the numerator and denominator are each product rule. So as you are taking the derivative of the top and the bottom, you're going to be doing product rule, and the product rules, you got power of a function in here, you got a couple of square roots, you've got an exponential function, you've got a lot going on. Okay, so this will probably take about 15 to 20 minutes for you to go through this. Okay, so I'll give you that time to try it. I suppose, unless we want to see an easier way to do this. I mean, there is an easier way. Should we talk about the easier way? Well, the easier way is logarithmic differentiation. What would happen if we took the ln of both sides? Easier, still not trivial. How can I use properties of logarithms to make this easier thing to take the derivative of? Because it's not easier yet. We can split this up into ln of 3x plus 7 to the fourth plus ln of root 9 minus x squared minus ln of e to the 4x cubed minus ln of root x squared plus 1. Now hold on, we can take this even further. I can take all those exponents out front. Plus 1/2 ln 9 minus x squared. What is ln of e to the 4x cubed? Sorry. Oh, hold on. I'm looking at something here and I've got something written wrong. So I'm going to fix this. This cubed, I got to fix this in my lesson because it's not obvious and I mess it up every year, even though it's my question. That cube is supposed to be in the root. Okay, so that's better. So what is ln of e to the 4x? Well, it's just 4x. So then this is minus 1/3 ln of x squared plus 1. Now that is a lot easier to take the derivative of. So we're going to go ahead and do this. I'm going to put the 4 on top times the 3, which is the derivative of the argument. Like, I'm going to actually speed this up a little bit. I've been taking my time so far. Derivative of the argument is negative 2x over 2 9 minus x squared. So this was the 1 over the argument, right, times the derivative of the argument, which is negative 2x, and then the 1/2 goes there. Okay. Derivative of negative 4x, negative 4. Same thing, derivative of the argument is 2x over 3. This is a great example of where if you can save a step, because it's a lot of writing, then that's a great thing to do. Save yourself a step by, by incorporating some of the fractions in your first pass through. So that's 12 over 3x plus 7 minus the 2's simplify, minus 4, minus this one does not simplify, and then leaving in explicit form. I'm actually gonna just quit here and not rewrite this again, but that would be y, and that would be the thing above it. So y would be in that bracket, and this thing would be in that bracket, right? So that's a lot easier. Now, again, like I said in the last question, if you had actually tried to take the derivative of that, and I really hope you never have to, without using logarithmic differentiation, you're going to get something that looks a lot different from this. Okay, and solving what we have here may not be very easy, may not work, like may barely be possible. We'd have to get a common denominator and do all sorts of crazy stuff, which we could do. I mean, that wouldn't be the hardest thing, but it would be a lot. And who knows what it would look like if I took the derivative of that and tried to clean it up. So that's not really something that we do. It's not really something that we worry about, but this is another example of when logarithmic differentiation can be very useful. Okay, takes product rule, quotient rule, and turns it into something that's not product rule, quotient rule. Okay, and that is logarithmic differentiation. We see that it's useful in a variety of places. Mostly we're going to use it for the kinds of things that have a variable in the base and the exponent, but like I just said, it's useful in other places. And it's the first time we saw putting it back in explicit form. And that's that, and that wraps up the unit. So good luck with the practice for this, and I think that's it.